All right, so last time we talked about how to add vectors using the tip to tail method. And we started off with an example. Let's say we have vector A pointing in this direction, vector B pointing like this at some angle. Maybe both are some arbitrary angle. A is relatively straight. So we said if we want to have our resultant vector, which is R equals A plus B, we take the tip of the first vector and add it to the tail of the second vector, which is B in this case. But if it was B plus A, same thing, B would be first and then A would be second, and should resolve to be the same thing. So this is our vector addition, where we took the tip of A, added to the tail of B. We then said if we want to find the resultant R vector, that we'd have to do the Pythagorean sum of Rx and Ry squared. And we also talked about how last time Rx is comprised of Ax and Bx to make up Rx, because the main vector here, R, resultant vector R, is A plus B. So therefore, the components of R are going to be the sums of the components of A and B, which is, stands to reason. So we were going through that. And so R is the sum of sums. So A is comprised of AX and AY, and then we do the Pythagorean sum of AX squared plus AY squared. And that's just an arbitrary vector A. And so if we have a real vector velocity at some angle, it has an X and Y component. And then we do the Pythagorean sum on Vx and Vy in order to get the vector V. So again, A is this way, B is this way, A plus B tip to tail method. And then the resulting vector is R, where we draw R from the beginning of A to the tail of A to the tip of B, and so on. And then we looked at section 3.4, components and unit vectors. We stated that vector A is made up of its two parts here, projected at some angle. And we know that AX is going to be A cosine theta, AY is A sine theta. It's like a right triangle. Magnitude, again, much like the Pythagorean theorem. Then we talked about finding the direction. We got the magnitude using Pythagorean sum. The direction is just finding the angle of that vector by using tangent, which is the standard, the convention, but you can use sine theta, opposite over hypotenuse, cosine, adjacent over hypotenuse, that sort of thing. And you get the same number, same answer, as we saw here. Then we looked at the different quadrants where we're trying to determine which components are going to be positive. We know in the first quadrant, all of the components are positive. Quadrant 2, only the sines are positive. The cosines are negative, therefore tangent negative and everything else will be negative. Third quadrant, tangents positive, and fourth, the cosine is positive.
Mr. Kelly?
Yep.
When, let's say, both the cosine and the sine are negative, so the angle will be the angle that's in the third quadrant, right? Like, yeah, the direction we're trying to find.
Exactly, and that angle will be with respect to the x-axis here.
So it will be plus whatever angle it is, plus 120, 180.
Well, yeah, and let's say that was 60 degrees, like it'll be 180 plus 60, which would be 240. But we're only concerned about the angle from the x-axis, so we'll just say 60 as opposed to saying 240. Although they have the same, their cosines are the same, right?
Okay. So we don't need to worry about it because we already know that it's negative, I guess, right?
Well, this angle here will be positive because if we go counterclockwise, this angle will always be positive. The angle that's going to be negative is the one with respect to the y-axis if we go backwards. So just to clear up any kind of confusion, we're always looking at the angle from the x-axis counterclockwise. So if you go clockwise, like this angle here, this example I was showing last time, that will be a negative angle because you're going against the flow of the conventional positive angles. You get that?
Yeah.
All right, so this will be positive and this angle here will be positive. All the angles, yeah. Well, this angle will be positive, but this angle here would be negative coming back. Yeah. So it's all. The convention is look at the x-axis, go in a counterclockwise direction. All the angles in a counterclockwise direction from the x-axis will be positive. So positive, positive, and this angle here coming from the x-axis this way will be a negative angle, right? Because it's going clockwise, but its complement will be positive. Yeah. Well, as long as you're going in a counterclockwise direction. All right, and that all becomes clearer once we take the tangent of whatever the components are. So we don't have to worry about that sort of thing if that's a little squirrely. So if we have a positive x here and a negative y, we know that the angle that we're going to get is going to be negative. So it all comes out in the numbers. So first quadrant, all sines, tangents, cosines. So then we talked about unit vectors, that they're just another way to express the vector components, the x and y components. X and y, x becomes I and y becomes j. So we could do something cumbersome like this, ax of I hat plus ayj hat, or just ai hat plus aj hat is the same thing as ax and ay, respectively. So the I hat unit vector, all the unit vectors have a value of 1, and that corresponds to the x-axis, j hat, y-axis, k hat, z-axis. Equals 1. And then we talked about this arbitrary position vector r, which is made up of the x and y components in the I and j hat directions, respectively. R is made up of x and y components. Right triangle, once again, just like the arbitrary vector r, it's just equal to a plus b, and some other arrows there for our arbitrary a and b vectors to make r. And this picture here was used to illustrate further that r, which is rx and ry, the rx's are made up of the smaller ax and bx, and ry, ay, and by to make up ry. And then you resolve all, you get the sums of x's and y's together, get all the x's together, get all the y's together, then you'll have your rx and ry's, and Pythagorean theorem, you have r. So we just showed it more explicitly here. R, which is equal to rx plus ry. Which is equal to ax plus bx plus ay plus by. Put everything together, and with the Pythagorean sum of x's and y's, you have the magnitude of r. So then we went on to our skills test as an example of that. So again, this was just more of the system of equations. I just put things together, show that R is Rx plus Ry, which is comprised of, Rx is comprised of Ax plus Bx, get some number, let's say it's 25, Ry is Ay plus By, 50, and then do your Pythagorean theorem. And that's where we left off. Okay, so let's go on to the next bit where we're, I guess I keep it in black. Subtracting vectors shouldn't be too bad. So all we're doing there is we're adding the opposite of a vector. Okay. So if we say something like A minus B, we are just adding the opposite of B, or B is now going to be in an opposite direction. A plus negative B. So before we had something like this, A is projected like so, and B, this is the geometry of R is equal to A plus B. And if we want to do A minus B, we keep A same size, same direction, and we take the opposite direction of B. B was once going this way, positive, or its original direction. Now the opposite direction would just be like this, something like that.
Could you go up a little bit?
Yeah. Okay. So you got that part?
Yes, thank you.
Yep. Yep. So yeah, if I'm going a little fast, let me know. So here is vector A pointing in this direction, and then the opposite of vector B, which is negative B, so positive, negative, and then we just do the same thing. R goes from the beginning of A, or the end of A to the beginning of B, and so that's the geometry for R is equal to A minus B. Any questions on that? So it's just nothing major, it's just the opposite direction when you do a subtraction. And so B being at a particular angle and A would just be itself. So in this case, the vector A, let's say we put this in a coordinate plane, right? A would be AX, right? So if A was at some angle, then you'd have to take care of that. But in this easy case, the vector A is the cosine or the X component. There is no Y component. B would be, or negative B would be at some angle theta with respect to our x-axis. Let's say we have vector B that projected this way, and we wouldn't use a supplementary angle. We'd always use the acute angle from the x-axis. That's something also to keep in mind. The projection angle is the acute angle from X. So we'd be taking a look at B with respect to this angle here. You guys following that? Did that make sense there? Okay, and our next bit we want to do is take a look at the geometry of multiplying vectors by scalars. Again, it's just 2 times the vector. So let's just take a look at that. By vectors by scalars. Say we wanted to see what the geometry or the picture is of a resultant vector R equals to some arbitrary scalar M multiplied by vector A. Geometrically, all we're doing is just appending a scalar onto a vector, right? So and the geometry of that is very simple. Let's say we have vector A pointing this direction, and then we just append some scalar onto it. That's the multiplication of M times A. Nothing major involved with that. There's one problem, I think, in your homework that works with scalars and vectors, but I don't see it coming up a lot, but it's something nice to know just in case you need it, right? So again, the scalar just is a value, just a number. It doesn't have an arrow to indicate it points anywhere. That's why I want to write this here. Notice that the scalar M is not, or doesn't even have, is not an arrow to show that the line here is not an arrow, it's just a line, it's a segment. A little bit back to geometry, segments, lines, rays, but we're just incorporating them all at once. So any questions on that? You guys following that okay? Need to write something. So yeah, just multiplying scalars onto vectors.
What if M or A was negative? One or the other?
Yeah, we just now we know that the scalar can't point anywhere, so we would just have to reverse. We'd have to reverse the direction of A to make it negative MA. Follow that? So if A now points opposite, and then M is still just hanging out.
Okay, just making sure.
Yeah. Yeah, because the only you don't want to get twisted with anything with M, because M is just the number is just hanging out in space. I could even put M over, over here, and A would still have to be pointing opposite, and you still get the same result. Because the most important thing is to change the direction of A, and then and likewise. Okay, so. Okay.
Mr. Kelly,
Yeah.
can M change the direction for the vector?
No, M is a scalar, so there's no directions to change.
Okay. All right.
Yep, that knocks that out. You have to change A to get that result. See if anything else, any other properties. We know the negative of vectors, so you can add and subtract. Let's do a sample subtraction. Let me move to my next bit. Okay, so let's say that make something up, huh? Or we could use an example from the book. But let's say that we had, we have vector A projected like so. And then, let's see. I want to take that one picture that we just had, right? And so this will be vector A. And let's say that this is, I'm just taking and putting it on the coordinate plane here. A is not just going to be along the x-axis, so we're going to generalize this. And B is going to be this way. We'll say it's negative B. And because, original B was pointing in this direction. And then R is geometrically going to be like that. So now let's append some values on A and negative B. So A is going to be 13 meters at 35 degrees from the x-axis. And then the negative B, 17 meters. It's not with respect to this angle, but with the x-axis going like so. Something like that. So let's say that vector B is at 75 degrees. Let's now calculate, sorry about that. Find the resulting vector R. Yeah, I mean, you guys could just stay right here. Have some other problems we can do in a breakout, but let's just take a few minutes and do this. Not unless you want to go to breakout. I could just have you stay here and calculate this.
Mr. K, could you repeat what's the red vector?
No, I was just showing that the angle that I'm choosing here, the 75 degrees, is with respect to the conventional x-axis. It's like for this vector B, I'm projecting it, actually, to be quite honest with you.
Mr. Kelly, doesn't it have to be a right angle, a right triangle?
No, it doesn't. What you're doing with the components is making the vector R into a right triangle. You're not doing right triangles all the time. The components of A and B will make the vector R into a right triangle. But A and B themselves don't have to be legs of a right triangle.
Mr. Kelly,
Yeah.
may I request that you walk us through this one? Because personally, I'm like a little.
Sure. No worries, no worries. Okay. That is absolutely not a big deal. What I was about to say here is that, okay, the x-axis, you know, if we chose, if this was like our vector b, right, negative b, and we were concerned on the orientation, like how to view where b is projecting from, it's always going to be the acute angle in this case. So like we have these two parallel lines. I'm not going to go into the alternate interior angles, all that stuff. But this angle would be an obtuse angle. So we're not concerned about that particular angle there. We're looking at this acute angle from this x-axis. So this would be our 75 degrees that's in question, which is actually the alternate of this angle in there. But again, you know, don't trip out on that. We are just looking at angle of 75 degrees. So let's walk through this. So R we know is Rx plus Ry. So ultimately, this vector R is going to have, if I can just draw this in. X and Y components, AX and AY, like so. And then B will have its X and Y components. That's going to start getting messy. I don't want to just draw that in. But the point here that I want to make is that Rx is going to be made up of AX and BX. Ry is made up of AY and BY. And our job is to figure out those pieces to make up Rx and Ry. And then once we know what Rx and Ry are, then we can use a Pythagorean theorem to find out R. And then after that, we can find the direction of R, right? So again, Rx is AX and BX, like so. Yeah, so, and then I wrote it up even further last time. So our job is to get that value. And then that comes out to be R, which is AX plus AY is A, BX and BY is, well, it's going to be the negative, obviously, sorry. So like that. Far so good? Do we understand that process so far? We are subtracting. So let me go even further so I don't blur any lines. Plus, so yeah. Now that's the abstract. Let's put in our numbers. Rx will be AX, which is a cosine of 35. I'll even be more explicit. A cosine theta minus B cosine theta. Say theta 1, theta 2. Different angles. Right? So Ry then would be a sine theta 1 That, you know, we're trying to get those, etc. So we're adding. This addition will be the addition of subtractions. Right. So again, our x, getting my numbers here, 1335. 13 cosine 35 minus 17 cosine 75. Got it? Thirteen sine 35.
Welcome back, Mr. Kelly. You're muted.
All right, sorry, my internet hung up on me. It just straight disconnected, and then it took me a while to rejoin.
No worries.
Yeah. 1 segundo. All right, I don't know if you saw this or not. Did you guys see this part?
We did not. Would you mind just pausing it there for 1 second?
Yeah.
Mr. Kelly, that you used 75-degree angle. Is that with the relationship with the x-axis?
With the x-axis, yes.
But isn't it like going west to south? Like, isn't it between 180 to 270?
No, we're not even making it that complicated. You can do all that stuff later once you have a general understanding, but it's all about x. So A here is projected 35 degrees counterclockwise from x. You're going unit circle style. B, we're going to use the acute angle of B, which is going to be this guy. That's arbitrarily 75. Not putting anything else on it.
So let's say B started from the origin. Would it be 75-degree again?
Yeah, it will still be 75. Because all we're doing here
with the x-axis?
With the x-axis. Because all we're doing here is we're reassigning a coordinate system for B. So B is somewhere out in space, but it has the same XY coordinate system as A does.
I just always measure the angle from the start of the vector but this time it's the end of the arrow.
It's the same difference. Okay, just to be clear on that, B projects from its own origin. So if we are reassigning B from its own origin, so these are different frames of reference. It's not that they have their different starting points, but they still have XY coordinates. There's X and Y for B. B starts here, A starts here, C starts someplace else, but you can always reassign XY planes for each vector. So B is here, so 75 would be there, which is my 75 I drew here, alternate interior. See that?
So if we use 75 instead of 75 plus 180, it's gonna be the same solution?
It should be, yeah, because we're looking at the...
So if I use
coterminal.
75 plus 180, I should get
Why would you want to do that though? Why?
Because you see the second XY.
That should
then
work. That
it
should work though, because it's a coterminal, and I believe that should be okay.
All right. Okay. Thanks.
Yeah, but again, I wanted to show this. That's 75. That's 75. That's 75. I mean, you know, now you have the what is this? The opposite angles are equal. Geometry comes back to play. Alternate interior angle. So what you want to do, that should work, but 75 is the easy choice. And I just wanted to do that to let you see an even bigger picture or a clearer picture of why we choose the x-axis and that sort of business.
Mr. Kelly, would you mind scrolling down?
Yeah.
Thank you.
Okay, so I think, yeah, we conked out right there. But, okay, so you guys, let's see, calculate this. So you get 35. So this first one should be 10.6, 13 cosine 35. Degree mode. 17. .4, which is 5.2. 6.2. Yeah. Okay. 6.2. Thirteen sine 35 is 7.45. Oops. And 17. That's 16.4. So we have our X, our Y, minus 16.4, 8.95, and we are ready to go. So Rx plus Ry, but that's not a straight up subtraction. We have to do the Pythagorean theorem on it, but this here just says what R is made of. It's got an X and a Y component. Okay, good. Linear combination. All right. Now to find the value. That will be, yeah. .2 squared plus, right? That all becomes positive. That's why we had an early question. If one of the vectors is negative, can R itself be negative? It can never be negative. It's a value. It's a vector with a angular direction. Square root of 118. That's roughly 10.86 meters. So that's magnitude, direction, Ry over Rx. You can already tell that the angle is going to be negative, and that actually goes back to our geometry of how we drew R. it's going to have a negative angle here because if we take from the x-axis and go the opposite way, clockwise, negative, right? Geometry fits, math is working. So this will be negative in this case. Okay. 1.44. Negative 55. Okay, so there's that. Any questions? Magnitude 10.86 at 55 degrees clockwise in the fourth quadrant, or 360 minus 55. Uh, 305. Going counterclockwise. So yeah, so we go this way, negative 55. Coles terminal, that is 305. Questions? You see that?
So just to confirm, the only difference between subtracting and adding vectors is that for this you add that extra line where you get 75 degrees, right? Whatever that's called. And then you do, instead of ax plus bx and then plus ay plus by, you're basically exchanging the plus for negative or subtraction.
Right.
Making sure.
That is it. And generally, you won't get these the geometries here. They'll just say, okay, subtract b from a, or b minus a, or something, or a minus 2b, something like that. But I just wanted to draw it out to get a better picture. Yeah. But yeah, I mean, it's all the subtraction is just the opposite direction. Okay. So with that being said, if there are no questions, I'll give you a problem or so to practice. Let us see, give you 10 minutes worth. Let's see, why don't we try number 31, page 67, part of your homework. We're actually applying the vector knowledge to actual physical situation. And try that out for 10 minutes, see what you get there. See you in 10. All right, any other questions? Okay, all right, see you later. Then let's see, 5 rooms. Okay, great. Whoops. So the thing like I like to do is get all my X stuff together, set it equal to whatever it's going to be equal to, get my Y stuff together, and solve that Pythagorean sum. What we're going to see when we get to chapter 4 especially is that we're going to be given the result. Either your forces are going to be equal to 0 or mass times acceleration, and it's our job to figure out what makes them up from the X components and the Y components. So it's very key that we get used to peeling apart vectors in their abstract form now. And this is like one application of these vectors for now. Okay, so number 31. So we have a force, somebody's pulling at this angle. Force measured in newtons, 120 newtons at 60 degrees from the x-axis. The other guy is at 80. So we could break it apart. F1 is equal to F1x plus F1y. F2 is F2x negative direction and F2y, or just start to get the x's and y's together separately. So, because at the end of the day, the force, the one force that's going to be the equivalent of these two is going to be the linear combination of F1 and F2, where F1 is going to be made up of x's and x's, and F2 is the x and y, and then F2 of x and y. So let's deal with that. So like I said in the beginning, I like to just get all my forces in the x direction, all my forces in the y direction, and then just sum them together. So all my forces in the x direction will be F1x, which is pointing to the right like so. And that's my y component. And then my F2x, which will be negative, and then my F2y.
So their x's are in opposite directions, but y's in the same?
Correct. Because what we're trying to do is make this ultimate right triangle here. So X, Y for F1, X, Y for F2. All right. Now we could, obviously this works, but what we could do is we could just add these vectors together, you know, in the geometry that we had before, where we have F1 plus F2, like we see here, and then all we have to, in that case, we'd have to just project F1 and then say F2 is like this, keeping kind of the same, I mean, it's not to scale, and then the resultant vector F or R, if you will, is going to be something like this. But I'm taking it at face value. I mean, there's a couple of ways to approach it. You're going to get the same result, either approach you take. Because this here will be 75. And this frame of reference here, if I may, will be 60. So that's just a little messy, as you can see there, but I just took it as is there. So all my forces in the x direction will be F1x plus F2x equals stuff. F1y plus, and we proceed. This is going to be 120 cosine of 60 positive, and then the other one will be 80 cosine of 75. My Fy's 20. Any questions there? Hopefully we have that so far. And you just calculate, and that's about it. So Fx 60 minus 20.7, 39.3. And Fy 103.9. $77.2. $181. Let's say 1. So the resultant will be everything in the X, everything in the Y. So we do this okay. Hopefully I added everything up, right? 34,215. This is approximately 185 newtons. Okay, hopefully you got that. You guys get that for your result?
I'm sorry, how did you transfer it into newtons? Oh, you just square. I'm sorry. Never mind. Never mind.
The unit of force is newtons, but
Yes. Sorry.
man, you can say 185. And then that's our magnitude. Direction 181.1 divided by 7.3. Okay. And so the angle is roughly 78.3 degrees. Some sig figs in there. I probably took liberties somewhere, and then I think at the 77, 78 degrees is the answer. And that's part A. Then part B said, what is the force that a third person would have to exert on the mule to make the resultant force equal to 0? The same force, opposite direction. So you add 180 to this, what Sin was asking about earlier. So if we have, resultant like this at approximately 78 degrees, 185, if you want to cancel this out or balance it, it's the same force, opposite direction. Newton's third law. And then also this first law, the sum of these two will add up to 0. So all the way over, that's 258 degrees. So you can express that 78 degrees, a negative 78, with respect to, the x-axis there. Any questions on that? And again, your geometry comes in. All right, actually, that's still 78.
Can you scroll up to where you found the angle?
Yeah. Right here.
Thank you.
So you're just doing Fy over Fx. The Fy component was 181, Fx 37.3.
So, Mr. Kelly,
Yep.
the third quarter, we can start from 0, right? So
Yeah.
if we can put 78 with positive sign, so we can start from 0 there.
Correct. That's still, if you say 78 degrees or 258, you're going to get the same result. Your cosine and sines will still be the same.
Yeah, but they're same but different with different signs.
Yes, different signs for exactly. Yeah. Because
that's the only difference.
The magnitude, yeah, but the signs would be different, yeah. The whole all signs ASTC. So that's about it. That's it for chapter 3, really. This is basics. And then next on Wednesday, we'll start chapter 4, which is more of the same. We're just now going to apply vectors into the beginning discussion of projectile motion. We're going to now see objects moving in an arc. And so we have to consider velocities, displacements, accelerations, velocities and displacements in the X and the Y direction. So now that we have some introduction here, hopefully that's going to translate okay. We start talking about projectile motion. All right, that is all. I'll have your skills test graded by next time. There's no other questions. We can leave early for today.
Mr. Kelly, so
Mhm.
you upload these recordings of the Zoom sessions to your YouTube channel?
Yes, I do. I will have this one up later on today.
Can I have the link for your YouTube channel?
Yeah, sure.
Because I don't have it.
No problem. So YouTube, you search for Dark Stat is the name.
Oh, all right, thank you.
Yeah. All right.
Mr. Kelly, I just have a
Yeah.
question. We had a skills
Yeah.
test last week. So that means we're going to have a skills test next week, right? Not this week, next week?
We are going to have one on Thursday. I think
Thursday.
And yeah, we meet 3 times this week, Wednesday and Thursday. So the skills test will be one every week.
Oh, okay.
It'll be every Thursday, not unless something else comes up.
Alrighty.
Okay.
Cool.
And I had a question here. Yeah, so thanks, Nicole.
Mr. Kelly,
Yep.
can you go to the angle part? My internet cut out. I didn't get the copy.
Okay. Right there. So again, Fy over Fx. All right, so I'll see you guys on Wednesday.
Bye, Mr. Kelly.
Hey, see you.
Bye, Mr. Kelly.
Goodbye, Mr. Kelly.
Bye.
See you later. Bye.
Mr. Kelly,
Yeah.
what does it say on the bottom part? Down. Yeah.
Yeah, I was just answering part B, and we got this already, 185 and 78. And the force that you need to exert to make this 0 would be the same force, opposite direction.
Mhm.
And you can say 78 degrees, the opposite direction, or 258 degrees.
All right. Right.
Mhm.
Thank you, Mr. Kelly.
You're welcome.
Have a good day.
You too.